Hello guys, this is the Lexer part of the series. So we were going through first I had an overview of the entire project, the compiler project. Then I had this calling convention cdecal and system v AMT64 calling convention and a little bit about assembly. And then we had this makefile, right? So so overview and then followed by prerequisites. So this would be the actual part where we'll be looking through the Lexer part of the compiling. So uh, so today also there'll be few prerequisites I'll just touch because I get that pure if you are looking through just pure C, as in when you are going through C programming, you'll not come across these concepts. It's only when you do a project you get through these concepts. So I'll be touching those concepts required for this lecture part, and similarly I'll touch related concepts in the upcoming videos because only I'll be touching Lexer right now. So similarly in code generation also there are certain things that need to be touched. So I'll touch the C related concepts which you need to know at that time. So right now it's only about Lexer. So last time we were going through these parts, right? This one. Last time in the sense when we were going through NASM and linker, right? So what does linker do? Linker does this part, right? Combining of multiple files, resolving external symbols, then assigning entry points, right? And this part, raw machine code generation is assembler part. Okay. So this is just a revision of what we had gone through. The 2 hour video I had upload. We can go through for the in detail, in detail depth about even calling convention as I explained. So I had made a 2 hour video regarding that topic. So coming to today, I have to touch these concepts. I'll touch one by one. But firstly, today's topic is Lexer. So what do we achieve through an SK analyzer? We build tokens, right? So we pass through the entire file or entire string and we build the tokens, right? So tokens as in what? Say we have this input string or file that we are passing. Now in this line here we have first token as int, then the next token is so let me separate it by commas, but comma is also a token, so that won't be right. Okay, so let me put a space. Your space is not considered as a token because we won't process it in the next stages, right? Like in the syntax tree or semantic phase, right? So space doesn't have any white space and tabs doesn't have any meaning associated with it. So, but semicolon does have a meaning associated with it because semicolon means end of a statement, right? So in my case, if you remember statements, each statement, like, yeah, this statement one and statement four are siblings, right? So that semicolon we have to take care. Okay. So that part will be taken care in the syntax part. And as I already mentioned that syntax and semantic is combined in my compiler project. So back to where we were. We have int, then we have x, and then we have semicolon. These are the tokens. So there are a total of three tokens that we have. Now the next line is this one. For this we have int a equal 11 and then semicolon. These are the tokens. So there are total of one, 2, 3, 4, 5, 5 tokens. So similarly, here we have operator and we have exit, and this open and close bracket is also a token individually. This open bracket is a token and this closed bracket is another token. Okay. And similarly, this multiplication is a token, this minus is a token, division operator is a token, addition plus is a token, and this entire 1, 2, 3, 4, 5, 6, 7, 8, 9. So this entire a token, this entire a token. So it's a integer literally. Similar, this also a token, one token, this one token, this one token, this one token. Okay. So now important things here to note is let's take this example where we have int a equal. So here int is a keyword. Okay. Then a is identifier. Then equal is an operator. Then this 11 is an integer liter, right? And this semicolon is a separator. Okay. And similarly, even my case, so in my case, I have included. So okay, let's go through the code, right? That'll be better. So in my case, I have so I have these keywords exit, exit, int, if, else, while, and do. So right now I have one, two, three, four, five, six. Six keywords I have. Okay, in my language currently, right now. And if you look at separator, so keywords, I have five keywords. Okay, five keywords. And operator, if you look at operator, I have division as operator. And now for division as operator, this division as operator, and yeah, plus as operator, plus equal as operator. So all of these are my operators. Okay. So I have plus, I'm just separating it by comma because there are lots of operators. So plus equal, then also have plus plus, but I have not implemented this in my syntax and semantic phase, but I have included it here. Similarly, for minus also we have minus equal minus minus. Okay. And this one, and multiplication equal. Yeah. This assignment operator. This assignment operator. This operator which requires two operations. Okay. And then similarly modulus we have modulus modulus equal. Okay. Then equals, which is assignment, and this is boolean, like left and right we have to compare it for boolean expressions. Then we have not equal, not equal. And we have less than equal. Actually, we have not as well. We have not, then not equal. So basically, this next means if we have these both. So CH is the current character, and next is the next character. Okay. So here we have done this one. Also, see, okay, I'll touch this part uh, after telling this. So not equal. Then I have less than equal, less than equal, then more and more than equal. Then this ampersand, uh, ampersand, where is it? This bitwise and this for boolean and okay. And we have bitwise or logical or boolean expressions. And we also have this one less than, which is used for Boolean expressions, and this for shift operator, and again this for greater, and this again a shift operator. Okay, so this is a right shift and this is a left shift. So left shift as in 2 power, it increases, as in if we shift by 2 times it becomes 2 power 2, so 4 gets multiplied. We shift right shift by 2 times, then it's divide by 4. Or if we shift 3 times, as in if we do this way, right? So x of this is going to be x divided by 8. Okay. So this operator. So these are the operators we have. Okay. And then we have integer literal, we have identifier and separator. Now separators we have, this is a separator. Yeah. Separator. This is a separator. This comma is also a separator. This bracket is a separator. So this closing is also a separator. It's also a separator. Look at this is a separator that I have made. Then this is a separator. And yeah, we have this comments also as you right. Comments is not considered as a token because it doesn't have any meaning in the syntax and semantic phase. So yeah, it doesn't have meaning in the semantic phase because in syntax we do look at, but we don't require to look at even in syntax phase as well because this is the part where we have to check if it is a statement or not. It is in Lexer phase itself. So in lexical phase itself, we'll ignore the comments if that comment is been like as in say we had this. Okay. So after this, we have to close this right. We have to close the comment this way, right? And in between, we can have anything in these comments, right? So this portion, this handling of after this part, we need the closing of the comment that is handled in the lecture itself. Okay. It's not done in the syntax piece. And since these comments don't have any meaning as such in the language, so we ignore it and we don't process it further in the next phases like syntax and semantic phase. Okay. So in a lexical phase itself, we ignore it. Okay. So we have comments, then we have see actually I had commented this line out. If you can see, I had recently updated this handle comments in Lexer. So because there's a conflict, if I apply this division operator would be considered even for even as an operator and also as a comment. So that's why I have to handle it properly. So it could be a statement or it could be a comment. So we need to handle it properly. So that's what I have done it. I handled the diction operator in statement itself. Okay. So these are the separators, I believe. Yeah, these are the separators I have, and these are the operate. These are the operators that I have. So these are the operators. Now we'll go through each of this. Okay, on handling it. Firstly, we'll start with the main.c file, right? This is the entry point for all of my functions, all of my functionalities. So, yeah, now it is time to go through these concepts one by one. Like we have this argc and argv that we need to go through. Okay, so this is the same repository I had made, right? Uh, this one, the GCC is some playground. So there itself, I'll upload this also. Okay. So I will create a case dots and in here let's make a studio knowledge. and void main uh, and our cat star and and C equal SH2 of and I equal 0 to I less than R C I plus S. Okay. So after I write, I'll explain what this tab R of minus P equal to I. Okay. That should be it. And so argc is going to take the number of argument. Okay. And argv is going to be a array where we can point on the argument that we passed. Okay, let me show you what I mean. So if you do GCC test 2.c, okay, in the argument, there should be percentage s. Argv, informal percentage t expects argument of type in. Okay, so I like to keep your eyes. So uh, now if I do a dot out, okay. So here count is going to be 1 and my arc of 0, arc V, arc of argc is going to be 1 and argv of 0 because I have only one argument, okay, at this point. Here it is, the argument is only a dot out. So that is going to be the output, okay. So you can see it. So instead of this, if I do say 1, 2, 3. So now I have two arguments. So arc C is going to be 2 and arc V of 0 is going to be A dot out. Arc V of 1 is going to be 1, 2, 3. Okay. So sorry. So using this, I can point out what all arguments are being sent. So if I do here 3, 4, 5. So now arc C is going to be 3. And we are going to have arc V of 0 as A dot out, arc V of 1 as 1, 2, 3, and arc V of 2 is going to be 3, 4, 5. So that's what it is. So this what I wanted to show because why this is useful. If you look at my compiler, you can see that I'll be using I'll be using this command, right? If you look at here, um, Okay, not here. It's computer. So this is the one I'm using, right? This is the command I'm using, right? As in build name, and this is my first argument, which is the binary. Build name is having the binary, my compiler binary, and my test files here, test.c. It's in this folder, right? So that's why I'm giving test slash test dot c. No such file or so is happening. This one, right? Zero, zero, plus, was this? Okay, let me try test.tc or test.tc, sorry. I'm going to see. Okay. So it has to pick this one, right? It has to pick this, that there are, see here now argc will be 2 and arg of 0 is going to be this, argv of 0 is going to be this, argv of 1 is going to be this. So using argc and argv I can pick my arguments. Okay, and through that I can pass it to FU. Okay, that's what exactly is been done here. Look at over here, argv of 0. Okay, not this one here, F open. So I'm opening that file. So argv of 1. So argv of 1, what? This one, right? So that's what exactly I have done here. I'm reading the file. So argv of 1 is going to be in this file. This file. Okay. Okay, so argc and argv is covered, right? This portion is done. So yeah, the last, the make file. I had shown this make file, right? And I had made a dedicated video for of make file, right? So there, I think I forgot to mention about this W all and W extra. So W all is for the common warnings that we show. Okay. And W extra is what are the W all is unable to cover, W extra will cover. So these flags are used for warnings. And then we have a G flag. So this G flag is for debugger. So we have GDB, right? GDB. So this a debugger. So for this we use the G flag, and then we have a optimizer zero flag, so which will disable the compiler optimization. That's an important step because your optimization, if you apply a O2 or O3 flag, which is to optimize, then you can't use your G flag to get the debugging. Okay, so to clearly get the debugging, we have to switch off the optimizations. Okay. So this also done. And rest, I think I had already covered all this stuff. As in the C flags is used, right? It's used here. So the C flags will resolve into this value. So basically this one will, this entire thing will be resolved into the value W all, W extra, and as I told, W all, W extra are used for warnings, and this hyphen G, this for debugger, and to get the entire debugging, we use the optimization zero. Okay, zero optimizations. So, okay, that's it. That's it for the prerequisites, I guess. Okay, no, we are not done yet. We have the main.c, we have argc and argv, followed by if open is for opening of the file, and then we have a perror. Okay, now we have perror. So, uh, now there's a difference between perror. So there's a difference. We could have used standard error, string error. Okay, string error. There's a difference between string error and perror. Okay. Uh, non-existent. Okay, let's rename this non-existent one, and let me run GCC test and see. So basically I made a file to show you p error and string error, str error. So both of this is going to see whether we have this file or not. Why? Because this, if this file is there, then it's not a null pointer. If it's not there, it's going to return a null pointer. And if it's a null pointer, based on that, I am printing these messages. P error says and str error says. Okay. So for str error, we need printf, and this p error, we don't need the printf. As you can see here, p error gives p error says, and then followed by the error. No such file or directory. But this str error, we need to place it in printf, and that's when it gets displayed. So both will do the same thing, but only difference is that for str error, we see both achieve the same goal. But only difference is that in p error, it will not, it doesn't use printf. So in str error, we need to use printf. Now there's a problem over here. So the problem is that, say, hmm, say I want to do this. Yeah. So what this does is, what are the output? As in the printf values will go into out.txt. Okay. So if I do this, if you look at out.txt, it gives this. So if I have another printf, say first print printf, right, slash n. Now this first printf would be printed, and since I don't have non-existent .txt, I have non-existent one.txt, so it's going to return a null value. So this portion of the code would be executed, not this one. Yeah. So if I run this now, so what will be printed? Only printf will be printed, right? So this portion will go in, and this portion will go in into out.txt. So if I run this, go into out.txt. Okay, first printf is not printed. Why is that so? Okay, that's not printed because I didn't GCC. Uh, let's let's see. I updated the code right, so the binary has to update. Then if I do a dot out and out dot ext, so I get code. Okay, and if I run it again, uh, so into out dot ext. Okay. So if I run GCC, it will update the binary. Then if I do this into printf into out.txt file. So now you see a problem here, right? The problem here is that if I have an error, that will also be printed into my log. So if I don't want that, I use perror so that it won't be printed out into this output file. This out.txt, we'll use it as a log. So if you want to log in the output into a file, we'll use that. So it's say in that log, we only want the results. In that case, we don't want the errors to be in that place. So that's not a good thing, no. Because again and again, if you run and if you have errors, that's not a good place to stay. Because a log should contain only data, right? So in that places, we'll use this perror. So perror will show in the terminal that we have error or such file or directory. Okay. So this will show up in the screen. This one will show up in the screen along with the error message. But if we use this, this will go into the log file as well. So that's why we don't use uh, str error into log file scenario. So okay, now let's just run this one too. If we have non-existent one, right? How that will look at and non-existent has hello from non-existent file. Okay. Of Iran GCC. Yeah. Out. So hello from non-existent file. So already that's it. So we have a while loop. We have a buffer of size 1024. So into that buffer. So what does a fread do? So fread is going to take that buffer which we want. Okay. And into that we are sending one by one character. Okay. One character after other, one byte after other. And until size of buffer minus one. So why is it size of buffer minus one? Because from 0 to what do we have? 0 to 1023, right? So this entire is 1024. But the last one we need to fit as null, right? Because say if the string size is String size is 3. So let's say hi is the string. Then h will take up at 0 position. I will take up at 1, and then finally at the third position you need to append a null. This is 2. Okay, and that's how the string termination. So similar concept here, up to 1023 I'll fill up, and in the 1024th location I'm going to append 0 null. So that is string terminates. So that printf, will terminate this percentage as we terminate that point. So okay. Um, okay, let's run this. And if so, how many times will this loop run? What do you think? How many times will this loop run? It will run based on the length of this buffer and also based on the length of uh, it will run based on this length of buffer and also based on the length of this file, right? So to demonstrate that, uh, this 1024, but how many characters do we have here? We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 27 characters. 27 characters. So 27 characters and 1024, which is highest. 27 is lowest, right? And 1024 is highest. So we'll stop. See, this while loop will stop because of that 27 characters. Why? After 27th character will reach. After the 27th character will reach end of the file. Okay. So when it reaches end of the file, it's going to return 0. F read is going to be 0. So that's when it will be uh, out of the loop. So let's just prove that, right? Let's just prove that by putting a printf that here it will only come once. Okay, this portion would be run only once. Okay, let's just prove that. Let's put a space here. So if I run GCC test.c, and if I run see what will printf do, it will printf the character one by one. Okay, and then we have this space, but this space didn't print up. It is printed right after this portion, right after the file here. It's printed and it came out. So it printed once. Now if I change this, let's say to 2. So in that case, how will be filled? So it will be filled like this. Um, it will be filled up this way. So after H, we'll have a space. After H, we will have a space. Why we will have a space? Because of because our size of buffer is going to be 2 minus 1, which is 1. So only H will be written. And right after that, we have 0. Okay. So this 0 will not be printed. Instead, this space will be printed. Okay. Because 0 means we have to terminate, right? So this space will be printed. Similar for E also, we'll have this 0, but then space will be bracket. So same for everything. So now I'll show you that instead of this, we'll have spaces right now. So uh, if I run GCC just dot C and see, you have that space. So what does that mean? So based on the length of buffer, we are visiting the block. Okay, the block portion we are visiting based on the size of the buffer. Okay, that's why we have these spaces. So if the size was bigger, then we wouldn't visit. If the size is bigger than, if the buffer size is bigger than the content in the file, then it can take up everything, right? So that's why it's not, it's only visiting the space once. See, that's the difference. So that's about this. I'll upload this file. I'll upload the update. I guess these two are the updates. I'll upload this into the GCC ASM playground. Okay, so back to this, back to our compiler. Back to our compiler. Uh, so we were into lexical phase, right? That's what we have to do right now. So, see, there is a certain rule that we have to follow right? In C. In C, we can't just keep writing functions. And functions has to be in its own files. So, in my case, Lexer based lexical analysis based functionalities in Lexer.c and Lexer.h will contain the functionalities which I need to make it public. Public means which I need to make it visible to my main.c. Okay. Main.c or other outside world. So if I want to make it visible, that's where I write into my header file. So like this free tokens, Lexer, print tokens. These are the functions that I need to make it visible out of the Lexer.c functionalities. I'll have more functionalities here, right? So it's not like I need to make everything uh, to be visible. Only some I need to be, some of the functions only I need have to make it visible. So the ones which I need to make it visible, I write it on my header file. Same goes for parser.c. So the functions which need to make it visible, I'm going to write it on my parser.h. Not just functions, even the tokens and enums. Sorry, not token here. Token is a struct. So the struct and enums as well. So if we look at in in.c, we are invoking. So these parts are done right. This for if we don't get two arguments, we are printing in that usage is that we need to provide a source file as well. So using argc, we'll tell that, and argv using argv will get the source file, and if it's not available, we'll say that file failed to open the file, right? And after that, we are calling in the Lexer. So this Lexer is in this file, lexer.c. Okay. This is the main function. And in this entire file, this is the main function. And this function internally calls all of these functions above it. Okay. So let me get back to what Lexer is. Okay. So here it's in. This one is also done. Mm, function pointer will cover it. Yeah. So what are the basic stuff we need? We need a keyword for a language. We need identifier. We need operators, integer literal, and separator. Well, in my case, we also have character literal, right? But in my case, I am starting with integer literal. So right now, I am only handling integer literal. Okay, so a token has to be int, int as in integer literal. Okay, and keyword is what? So int is this portion, integer literal. Then keyword is what? Keyword is this, right? We had these keywords, right? Five keywords we had. So what all keywords did we have? So these are the keywords: exit, int, if, else, while, do. Okay, these are the keywords. So I made an enum by the name token type. So that token type will have int literal, the keyword, the separator. These are separators, right? These are separators. These separators, integer literal, keyword, then identifier. Identifier is important, right, for the variable creation. Then we have operators. Operators are also equally important so that we get to evaluate expressions. And and then finally we have string literal. I have added this, but in the entire project, as in I have not handled this part in my syntax plus semantic phase. So as of now, these three are functional. One, two, three, four, five. Five of these are functional. Okay. So in future, I'll be creating string literal as well. Okay. Uh, so back to this one. So from Lexer is the entry point to the entire functions within this. Okay, within this file. So if you go into Lexer is the entry point to all the functions within it. Like we have print token, we have okay, and we also have we also have this line, this comments. Okay, so wait, so firstly I have to come back to the basics. Basics as in so Lexer. If you look at Lexer, it's a finite automata. Finite automata. So a finite automata can uh, it can solve Lexer kind of problem. Okay. So why? Because we have to look through keywords, right? The keywords like int and what else we have. After int, we have exit, while, do, if, else. This we have to pass, right? Except for this, other than this, right now in my language, other than this are not keywords. Similarly, identifier. An identifier has to start from a letter. So let me denote letter by L. Okay, L, and followed by it can be a letter or a digit, or it can be just a letter, like in A, right? So it can be followed by a letter or a digit and any number. So star represents any number. So it can be zero or it can be one or more than one. Okay. Zero and greater than zero. Okay. This is your identity power. So there's a common thing between keywords and uh, identifier. Both of it starts from letter, right? So both of it starts from letter. But see, for integer we have to go through each, as in I, N, and T. Even for exit we have to go through E, X, I, and T. Even for while we have to go through W, H, I, L, E, and do is D, O, I, F, E, L, S, E for if and else. Okay. Now, if we have something like int 1, this will become an identifier. If you have exit 10, this will become an identifier. So these portions we can handle using finite automata or a regular expression or a regular grammar. Okay. So that's what we do here. So a simple if and else case can handle entire lexical analysis. So how is it done? Similarly, even for your separators, you look for this opening and closing, right? Closing separators, closing brackets, which is a separator. Again, this opening and this closing, and also this semicolon and this comma, right? So all of this will be going through, right? So if you do a string comparison and you check using if, the entire lexical analysis is done. So that's what exactly has been done here. So using a simple if check, we can cover the entire lexical analysis. So if you look at here, so I have character ch. So it's going to get the character uh, one by one, f get c. Okay. And I'm going through the file until we don't reach the end of the file. So this entire while loop that I'm running, this entire while loop. So this while loop can think of like a state machine. So let me show, right? Finite automata. You can think of this while loop, okay? This entire while loop, and this entire while loop as starting from here, then going this way, and throughout this, uh, uh, not this way. So you have an entry point. Okay, you have an entry point. Then if it's a in here, if it's a B, you are staying here, right? And if it's a A, you are going here, then B. So there's a continuity, right? You are going through the say the string is like this. So if it is a B, we stay at B. Okay. So let me denote by B star. Okay. After B star, if we get a A, we reach state 1, right? So this state. Then after A, we go to B. So B. Then actually we have a BA star, BA star or AB star. We have a BA star. So we have a BA whole star plus BA whole star plus A star. Okay. And then from here, B and B, WB. So we'll reach the final state here, right? This is one of the expression that gets uh, to the final state. Similarly, we also have this one A, B, B, and B. have B star, yeah, A, B, A, B, B. So three B's. This whole star. uh, And in between this A, we have a star as well. A star. And in between, we have a B, A star as well. Right? B, A star, followed by B, B, A star, followed by B. Then again, here a B, right? Then one more we have here, double B, A, double B, A. Yes, double B, A. Yeah, and we reach here, and followed by A double B. So this is the expression. So if you look at, we need a while loop. Why we need a while loop? We need a while loop to reach till the end of the file, right? So if you look at this A star is like a while loop, right? Because it's zero or greater than zero, right? So to get that sense, we need to run a while loop. So for zero or greater than zero, we need a while loop, right? And within it, we'll have a condition. So we'll have a condition like if B, then we stay at that point. And if we have this one, B A star, then we stay at a state. Or we have A star, we stay at a state. Then if we have double B, we reach at the final state and the string get accepted. Exact same way, we'll look at uh, firstly, here this is a theoretical concept. In practical way, we have to use malloc and realloc, right? Why we need realloc? Say, see here we have a capacity. So if you look at capacity, we have an initial token capacity, which is defaulted to 64. Okay, 64 bytes. So 64 bytes. 64 into, no, not 64. So 64 tokens, size of token. Get this token. So initially we are starting with 64 tokens. Okay, we are starting with 64 tokens. Then after that we look at, so tokens is a array of token. So initially it will have 64 tokens. So this pointer is pointing to 64 tokens, 64 consecutive tokens. And this count is going to count the number of tokens that we are passing in. Okay. So if it's equal to the capacity or greater than the capacity, we are doubling the capacity and we are doing realloc so that we can also fit in the tokens, the next tokens that are coming in. Okay. So as I was telling, in our case, instead of this B A star, we have keywords int, exit, while, do, if, else, and we have identifiers. Also, we have these, right? See, tokens are these, right? Tokens are integer literals, keywords, separators, identifiers, and operators, right? So that's what we are doing here. Also, we have new line. New line is also a token that we need to consider when we come through new line. New line, when we come through, we have to see. I have a global. See, new line is not considered as a token, but I need that new line to increment my line number. because see, it would be easy for the user. So, say for example, I am test 9.c. Okay, .tc. Okay, now it's saying that at line 1, it is expected that I have to put a semicolon. Okay, so similarly, if I now I put a semicolon, let's say I didn't put a semicolon here. So if I do that, it will say line 2. So this sense of that increment should happen, right? See here, I don't have this semicolon. So it has to pinpoint and tell the user. See, we are developers, but our end user is going to be a programmer who's writing this high level language, right? So with respect to them, you have to show them that this line number 2 is where the issue is. You have to put a semicolon there. Okay. So we are developer, compiler developer, but the end user would be a user who is using the high level language. So we need to pinpoint and tell them that this is the location, that they messed up. So that's how we have to properly tell that. So for that reason, so when we have a new line, so see from after the semicolon we have a new line, right? So when we have a new line, we need to increment the line, right? Line and column. See, this is line. See, this is line 1, this is line 2. But if you look at column, this 1, 2, 3, 4, 5, 6, 7, 8. So at eighth column, we have semicolon. So that's about line and column. That's why I created a global variable here, line and column, initialized as 1. Okay. So that way, if you look at uh, so this portion is nothing to do with our finite automata. This check to just increment the line and set the column as 0. Okay. So line plus plus, we have to increment the line when we get new line. And space, as I mentioned, space, white space, and all those tabs shouldn't be considered as a token. So I'm skipping that. Okay. Now, when we get a semicolon, now that's a token. So that's a token. So you can consider this semicolon as this B or this A. Okay, it's a separator, right? So we did a if. See here we are doing if B. See what we're doing here is for this language we are doing if B. Okay. Then we'll stay at stay at state 0. 0. Okay. But if we get like one more B. Okay. So let's say our current capital CH equal to this and next character is also B. Then we go to state 1. Alright. That's what is happening here, right? B, okay. We have A, B here, right? Here we can, here it is A. So next, so CH equal to this and this stay at this one. If CH equal to B, okay. stay at state 0, right? So this is how we are doing for this line, this expression here. But in our case, we need to pass in the token, right? So for that reason, this semicolon is a separator. So our action, instead of this state 0, our action is going to be that if we get this token, which is a separator, we need to say that it's a separator. We need to store it as a uh, separator token. So we made a token. Okay, token is this one. So in token, I have a union. Okay, I have a union of integer and string value. So what I use union. So token can be what can token be? Token can be a integer literal. It can be an identifier. It can be these things, right? It can be a keyword. It can be an identifier. It can be operator. It can be integer literal. So among these, see, integer literal is the only one which is integer. Rest all are strings, right? So that's why I'm using union. So what will union do? Union is going to compress your space, right? So max among string value, pointer and integer value. So max among them is going to be considered as the union. So it's not going to be, see, if integer is going to be 4 bytes and your character pointer is going to be 8 bytes. So entire union is going to be 8 bytes. See, if int is 4 bytes, okay, and your char pointer is 8 bytes. Why will it be 8 bytes? So remember I told you about 32-bit and 64-bit architecture, right? So in 64-bit architecture, it is 8 into 64-bit architecture. See how much is a byte? 8 bits is a byte, right? 8 8 so 64. So that's why addresses in see char pointer is going to be a address, right? So pointers are going to be 64-bit in going to be 8 bytes or 64-bit in 64-bit architecture. But in 32-bit architecture, it's going to be 4 bytes. Why? Because if you look at 4 into 8 equal to 32-bit, right? So 1 byte is 8 bits, and we have 4. Okay. 4 into 8 is 32. So 4 bytes is the pointer size in 32-bit. Okay. So here, if we use union, it's not going to be 4 plus 8. It's equal to 12 bytes. Okay. It's just going to take up 8 bytes. So this 8 bytes is going to be common for both the integer value and the string value. Okay. So I have a token type which will tell whether it is an integer literal, keyword, separator, identifier, or operator. Using that type, token type, I get to know what type of token it is. Okay. So that will be useful in my this is going to be very useful in my syntax tree. Okay, syntax and semantic phase. Uh, syntax tree will be most useful. Okay. And this value is going to be this, right, which I told. Value is going to be, see, value is going to be a keyword or an identifier or an operator or an integer literal. Okay. That's our value. And then we have the token where it is the line and column number that will be useful for our end users. Okay. So that particular token, we'll mention that it is at this line and this column. So if that particular token. Say in semantic phase, it's not defined. So say I run this test 3 because see, this token will be used in our syntax and semantic phase as well, right? So if I run this, it'll tell that un, undefined variable y at line 1. Okay. So this, if we have to pinpoint, I need this line number and column number as well. So that's why line number and column number. So the token type is necessary. Also this value, then line and the column number. So these are necessary. And then back to our part where we had this semicolon. Okay. So semicolon is a separator. So separator and is this is a string duplicate. Okay. So it's going to duplicate this string and it's going to assign a particular location in memory, and that location is passed on to string value. So this string value is pointer, right? I told you it's pointer, right? That pointer will have this location where this value will be stored, the string will be stored. So I did this for safety case. So we have to see we are using it. It's this str string duplicate is going to be using internally malloc. Okay, so we have to clean up as well. So that cleanup is done through this. mm, it's done through this free token. Okay, so you can see I have used uh, free token value str. So I'm freeing it and I'm setting it to null. So it's important to clean that as well when we are coming out. So this semicolon, similarly, we have comma, then we have this open bracket, these open brackets, then the close brackets, which are again all separators. Now, see here, uh, this one can be confusing because it can be a division operator or uh, uh, it can be a division operator or a comment. So that's why we have to carefully look at ch. Okay, ch could be, this could be division. So we take a next pointer with f get c. F get c gets the next character, right? See this here also we did ch, right? Ch earlier, ch f get c. So f get c will point to the next character. So so let's say ABC is the string. So right now we are starting. So ch equal to A when we do f get c. Next, if we do f get c, see like if we do this, so ch equal to A. And next time if we do again f get c of this, so say we are in a while loop, this line is within a while loop. So then it will take up B, ch equal to B, and so on. So it will become C, and then finally it become end of file or null character, this one, right? Null. So that's how fgetc works. So that's why we are going through here next. So why we did the next? Next, we are seeing whether it's a comment or not. So if it's a comment, so it's a single line comment, right? See, this one is a single line comment, right? This is a single line comment, this one. But this one, if you look at this, this is a multi-line comment, right? This one. This one is a multi-line comment. This is a single line comment. So that's what I'm doing here. So again, the comments won't be considered as a token. So uh, we are just skipping that step. We are not considering it as a token. We are just we are just passing through the comments, just checking whether it's properly aligned or not. As in, see, for single line comment, we check this. For multi-line comment, we have to check whether we have this star followed by this. So if it's not the case, we have to print a error message saying that the comments is not been handled properly. Okay, so single line comment, we go until we get end of file or we get until it's not a new line. Your single line comment, we have to be careful, right? It should be like this. See, like, yeah, say this is what we have. So after literal, we have end of file, right? Because next we don't have anything, so it's end of file. Also, in this case, we have a new line. So in new line, we'll reach this line 14. So new line or end of file. Okay. So that's why here, while it is not of end of file, or while it is not, and while it is not a new line, until then we need to plus the columns, right? We need to plus the columns and also the lines. If we have a new line, we need to go to the next line. So why we need to plus the columns? We need to increment the column to say that at a particular column we had an error. So that's why this column and line are necessary. Fine. So when we have a new line, we are going to increment the line and set the column to 0. And similarly for multi-line, so multi-line, we look at instead of next character being this, next character stop this was single line, right? This should be for multi-line. So if we get that, then we pass to the pass to the skip multi-line comment. Okay. In which case we will go up to end of file. Okay. And here new line also works. Only end of file should see for multi-line comment. New line also works, right? See, all of this is within the multi-line comment, right? So new line also works. So only end of file is the termination condition for multi-line. So that's what is being done here. See, previously we had for single line, we had even new line as well. We have to check. Here we don't have to check for new line. But if you have a new line, we have to anyway increment the line to pinpoint the location where we have the error. So remember where I told our end user is the user who is going to write the program in our high level language, right? So to those users, we need to pinpoint and say at this line and this column we have the issue. Okay. So for every new line, we'll increment the line and set the column to 0. Okay. It's like we need to reset the column, right? See, for every new line, we are starting from here, right? Again, we are starting from here, right? See, here we got a new line. After the new line, we are starting from 0, right? But line number got increased. That's all. Okay. So that's why we are resetting the column to 0. Okay. Then until when we have to go? Until we reach this. Until we reach, until we reach this and followed by this slash. Right? So if ch is this and next is this, that is when we are going to successfully close. Okay. So this is our script multi-line, which is not going to be uh, token. Okay. So comments are not tokens. So we are checking for this, right? If it's not the case, it's not the case, we are doing an unget C, right? See, we are doing unget C, right? So we are checking if we got this, then unget C. So when do we do unget C? What I need to say is, see, for multi-line comment, single comment, and division operator, the entry point is this. So I have to handle it properly. So if I have passed this next, okay, so if next is not this, okay, so currently we are at this first line, ch equal to this, okay, that's why we entered this position, right? We entered this place, okay. So if next is not this or next is not this, that is when we get into this location, right? So see, now division operator, we can have this or we can have this. This is also an operator, right? This is an assignment operator. So that's why I created this two nulls, so that I can cover this one as well. So the equal to will be placed here. So that's why I created an array for division equal to as well. Division equal. This equal will fit in here. So if the next is equal, so this operator would be satisfied. So OP of 1. OP of 1 is what? This one, right? So there we'll place this equal. Okay. And if that's not the case, we are going to unget C. Why we are going to unget C? Say if it was like A divided by B. Okay. So A will be identifier. So we didn't reach the identifier at, let's say we are at this location now, CH equal to this. And the next is what? Next is B, right? So next is not equal to operator. So that's why we'll go to unget C. So we'll unget C and we'll decrement the column. Okay. Why? Because it's a division operator. So it'll stay as it is. But if it was equal, if it was like say A equals B, okay. In this case, when CH is here, okay, when CH is here, next it's going to be is equal. Okay. In that case, this is going to get updated into this one. Okay. But in this case, it's not that scenario, right? So that's why we'll unget C. So ungetting C is we are so we had the pointer here, right? So when we get C, say we have A, B, C and followed by semicolon. When we do F get C, when we do F get C, right? Here we had next. When we do F get C, it'll say right now next was B. CH is this, next is B. When we do F get C, the pointer points to the next character, which is our semicolon. Okay. So we need to unget that, right? Because we need to reparse it and assign, we need to reparse this separator so that it gets assigned as a separator. So that's why we are going to unget C so that we'll point to this B back. So we need to unget B. So 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 that's exactly what we're doing here. In our case, we need to unget this one, right? If it is not, see if it is either this case or this case, we need to unget, right? If it was next equal to this, then we can assign. Otherwise, we unget. So if it is just 8 divided by b, we need to unget, right? And see here in the else case, which is for division or assignment operator, this is where we assign the token. So here we don't assign the token because comments are not tokens, right? We don't see comments don't have any role in the syntax tree and semantic phase. Syntax and semantic phase doesn't have any role. That's why we don't make it a token. So that's what is been done here. So see the division part, we are handling it here. See, I could have written it separately. This is the case where I'm handling for all operators. I could have done it here, but then it become double check. So I wanted to do a single check. So that's why I brought in the operator here itself. Yeah. So next one is strchr string char. Okay. So if the current ch, okay, the current value of ch is matching this, any of this plus or minus or any of these operators, that's when it will come into this part. Okay. So here we have all the operators plus equal minus equal plus and minus I haven't handled. Uh, right now I haven't handled. So I'm handling it by plus equal operator itself. Okay. So and minus also I'm handling it by minus equal operator itself. So minus equal minus into equal all of this. So all of these operators, all of this. So see what this means is this one. What it means is this op. Okay. Similarly, what this means is this operator. Okay. Similarly, this means this operator. Okay. So because ch is this, next is going to be again f get c of that file. Okay. And this file is which we had passed here, right? Argv gets this file, and this file we are passing it into Lexer, right? And number of tokens we get from Lexer itself, because number of tokens will be used in the next phase or the syntax. So here in the parsing phase, so syntax plus semantic phase, right? Uh, so back to this. So these operators are being considered. Now, see, I also have, um, hmm, see, we have operators like this as well, right? This one. See, there's a difference between this, this one, and this one. So what's the difference you can see? This length is 3, right? So that's why I have to handle this case separately. This one and also this one separately. Because its length is 3, so it has a one extra character, right? So that's why I have to handle this kind of separately. So if so I have operator, right? Operator. So that's why I have assigned operator 4, right? Operator of 4. So as in 4 characters. So, uh, so the third one is this one. Third one is this one. So I have to handle this. So if the current operator is this one, so this case, or if it is this one, this case. So and if the third one is this third one, again I'm doing a f get c, and third one is this equal. So then I assign operator to see this 0, 1, 2. At 0, I'll have either this one or this, and at 1, I'll have this one or this, and at 2, I'll have the equal rate. So that's what. So at 2, I'm assigning this. Else, we are going to unget C. Else, when will we do? Say we have A, B, or B, B. Okay. That's when we do get, right? So for P, we are going to do and get. Okay. And here we have white space. So white space is handled here, right? This is space we had right here. Uh, this one is space is handled. So after is case, we'll have this B, right? So that's when we'll enter here again, and we'll see that it's not this one, right? It's not this equal, right? So that's when we see that it's not equal. In which case, we'll see that no, we have to unget it, okay, and we have to minus the column. So this case has been handled here. So that's why we had operator count as 4. This array is 4 character long, right? So finally, this entire case here, this case here, these are all operators, right? So that's why I'm handling it as token.type as operator, and the string value is going to be this OP operator. So that we are passing here, and the column is this start column. This start column initially itself this call value I'm assigning here. Okay. So that one I'm passing here, and the line number token line. Okay. And here I'm printing as well. Okay. And this count plus plus, and I'm assigning into tokens this token. Okay. Next is digit. So here is where I have to see for see let me show this. See here base is 10, right? This is a base 10. This is a base 16. This is a base 2, and this is a base 8. So I'm how I'm telling all this, and this base 10. How I'm telling all this. See here by default it will be considered directly if you are not starting with 0 or 0x. 0x is for hexadecimal, 0b is for binary, 0 is for octal. Okay. So if it's not appended by 0 or 0x or 0b, by default it's going to be decimal. So here we need to bring it to a common base. So that is being handled over here. This portion, this I'll say. Okay. So that how I'm handling using, see, firstly, the token type is going to be integer detail. So that's why int, and we have the start column, then line, and then again this token should be put into this array. Okay. So generate number. Huh. So here now we'll come into this concept. this concept, the function pointer. Okay, function pointer. So function pointer, why we'll be using function pointer when we explain in a moment. Okay, so if it is appended by 0, then we'll look at if it is hexadecimal, because 0x is going to be hexadecimal and 0b is going to be binary and just 0 is going to be octal. Okay, so if you look at here, I have created a common parse number in base. Okay, it is common to this 0x, this 0b, and 0, this 0. If it is just 0, it's going to be octal, right? And also I'm going into else case. So if it is character is not 0, I'm going directly into decimal, else case, decimal. Okay. So if you look closely here, I'm passing in the file column, the base 16, if it is 0x, and I'm passing in is hex to digit, and first. So what is first here? If you look at first is that first number that we get after passing 0x. Okay. See, like for in this example, after 0x, the first number that we get is 1. So 1 will be first. Okay. So similarly here first will be, if we look at 0b here, 1, after 0b we have 1, and after 0 we have 1 again. So for octal that is the first. Okay. Okay, so not first, I have used next. Okay, I have used next instead of that one. Okay. Next itself I can use here, right? Yes, next itself I can use. So it's the common function and I'm reusing it. And here for decimal I'm passing in 10 and the ch. Right. Why I can pass in ch? Because it's not starting with 0. So ch itself I can pass in. Because for decimal it starts the non-zero. So 1, and here also 1, right? So directly it goes to decimal location. So here how function pointer is important here. I'll come to that. See, this one is our function pointer. So how? This is a function pointer. It's a pointer to a function. Okay. So if you look at, I'm passing in the file, the column, the base, the this function pointer, and this one. So why this is important? I could have written, a separate hex number or a octal number or a binary number or a decimal number, but instead I'm reusing. So this reusability is important in if you are working in an embedded system where space is a limit. So this reusability in in general scenario also it's very important so that your space gets reduced. Right? So if you look at here, I'm reducing the lines of code because I'm reusing here. So if you look at this one is valid digit function. So this is where if you look at, I have this is hex digit, is binary digit, is octal digit. So individually if I go in and is hex digit. So firstly it has to be is digit 0 to 9. Then it has to be A to F. Okay. And for binary, For binary, it has to be either 0 or 1, right? For octal, it has to be 0 to 7. And for decimal, it has to be CH. Huh. For decimal, it has to be each digit, right? Each digit. Okay. And how do you convert it? How do you convert it? So for binary, CH minus 0, right? After the check is been done, we know that the number is going to be 0 or 1 if it is binary. So we can do a simply CH minus 0, right? So 1 in ASCII is going to be larger than 0 in ASCII. Okay, 0 character. So 1 minus 0, I am going to get 1. Okay, so what I'm going to say is 0 character ASCII value is 48. So if you look at 1 character ASCII value, it's going to be 49. So 1 in ASCII is 49 and 0 in ASCII is 48. So 49 minus 48, that is going to be the result over here. If CH is 1, if CH was 0, it is going to be 48 minus 48, which is 0. So similarly for octal, we are going to do 7 minus 0. Firstly, we have to know that if it is octal or not. So 0 to 7. So 0 minus 0 is 0 and 7 minus 0 is 7, right? So all of that will be handled over here. Similarly for decimal, also we'll do CH minus 0. Okay. And like hexadecimal, here we need to have cases. So CH minus 0 and we need to do CH minus A because A is what? A is 10, right? See, in, in hexadecimal, we have 0 to 9, then A to F. So this A is what? This A is 10, then B is 11, C is 12, D is 13, E is 14, F is 10, right? So this A is 10. So that's why if we get A minus A is going to be 0 plus 10. Okay, so that is 10. So that's what. So F minus A. If we look at 102. Okay. And if we look at so 102. 102 minus if we look at the value of A is 97. So 97 plus 10, that should give me 15. Okay. So if you do 102 minus 97, that's going to be 5, right? 5 is 10 is 15. So that's why. So that's why we have to handle this case differently in hex. In octal and decimal and our this binary, it's easy. But in hexadecimal, we need to handle it this way. So now all of this, I can call it from a common point, which is sparse number in base. Okay. Now what will this do? This will take the number, okay, number into the base. Okay. Whatever the base we had passed on. Base could be 10 to base 2 binary, base 8 octal, base 16 hexadecimal, or base 10 decimal. So that base number would be multiplied and then two digit. Two digit is what? Two digit we are passing in a common entry point, right? So this two digit is going to be, it could be hex or it could be our binary. Like if you look at here, this binary, this binary or octal, or it could be this decimal. So this is a common entry point for all cases. So that's why if you look at, we are multiplying by the base, okay, and two digit. So two digit will internally call. See, two digit is again, what's two digit here? If you look at two digit, this again a function pointer. So this will internally call whatever function we have passed in. So if it is hex, so if it is hex, so hex two digit will be called. Okay. If it is binary, so binary two digit will be called. So we have this, right? So hex two digit will be called internally, or binary two digit will be called internally. No, it's called here. So see here two digit, if hex is the case, hex two digit will be called. So two digit would be replaced by hex two digit. If it is decimal, decimal two digit will be called. If it is binary, binary two digit will be called. So then that internally would be would return these values as I discussed, right? So if it is F, it's going to be written 15. If it is A, it is going to be going to return 10. So if it is not hex, if it is decimal, so it will return this CH minus 0. So it's going to be returning values 0 to 9. And here values from 0 to 7 for octal. Okay. So this is the common entry point. We are going to multiply the base. Uh, so this was the digit. This valid or not is valid. Is valid check is being done here. Okay. So is valid will internally call is this one is binary digit or not, is octal digit or not, is decimal or is hex, and this is passed from where? From here, from this. Okay. So this is hex digit would be replaced over here for this one is valid will be get replaced by the is hex digit for hexadecimal. For binary, it will be replaced by is binary digit. Okay. So first we need to check if it is that valid binary digit or hexadecimal or decimal or octal. After that, we'll do this base multiplication and the digit, right? And then we'll do a column plus because we need to increment the column. So if you have like, and we okay. So when we are here, we need to increment column, right? So when we are at 1, we need to increment, again we have to increment, and we have to reach B. So we need to increment column, right? So that's why we increment column. And then if it's not valid, see like this is decimal, right? After this, we reach at comma. So it's not a valid decimal, right? Then we do unget C and we do column minus minus and we break out of the loop and return the number. So a number would be stored here. So let's look at a case. Okay. So let's say we are dealing with this. Mm, let's say our number is octal. This octal. So when 0100 comes in, first we'll go to here. We'll see two digit. Okay. So two digit. So two digit is what? Two digit. If you look at, see, firstly it will go to 0, right? And it will come to this case, this else if part. This part will come. Okay. And then uh, two digit is going to be up two digit. Okay. So ch minus 0. So CH is going to be 1B. CH equal to 1B, right? CH is going to be 1. So that's what happens here. CH is going to be some number is equal to 2 digit of initial digit. Initial digit. So CH is going to be 1. So if you look at number here, um, here number, we already got the number here. Okay. So this initial digit. So number is going to be 1 here. Number is going to be 1 here because we passed in, right? So if you look at uh, so the next after 0, what is next? After 0, what do we have next? After 0, we have 1, right? So 1 is going to be passed. Okay. So when 1 is passed, we are going to do initial digit. So initial digit is going to be our 1, this one. And if you look at uh, this octal 2 digit, it's going to return 1 minus 0, which is 1, right? So 1. So number equal to 1 right now. So right now number is 1. Okay. 1 into now base. Base is what? Base is 8, right? So 1 into 8. Okay. Then next is 2 digit of CH. Okay. So before that it should be valid, is valid of CH. So if you look at here, after 1, if you do get C, because CH does get C, right? F get C. So if you do F get C, we are at 0. So 0 is valid, right? So then we do 0 plus 0. So which is 8. Okay. Now next again we come into the loop. Again we see that after this 0, we have this 0. Okay, again it is valid. So now 8 into, because number was previously 8, right? Number into base. So 8 into 8. Okay. Plus now again we have 0. So 0. So which is going to be 64. Okay. So now 64 is the number, and we see that after this one, we have a closing bracket. So that is not a digit, right? So it fails. So it fails, we'll unget C and get out, and we pass the number 64. See, 0, 1, 0, 0 is what? 64 only, right? And it's 0 plus 0 into 8 plus 1 into 8 power 2. So 8 power 2 is what? 8 into 8 is equal to 64. So this is 0 and this is 0. So 64. Okay. So that is how this for octal. Similarly, for our hexadecimal, instead of 8, it's going to be 16 over here. For decimal, it's going to be 10 over here. Okay. So this is a common entry point for all bases. These function pointers resolve into the particular functions. So either into hex to digit, or is no hex to digit, or decimal to digit, or octal to digit, or binary digit for this case, for character to digit, and for is value digit function. So it would resolve either into is hex digit, or is decimal digit, or is octal, or is binary. digit, right? So this how function pointers work. This is an important concept that you need to know. Okay, so that's how generate number will work. This how the entire integer literal be resolved. Yeah. Now back to our lecture. So we covered what all did we cover right now? We covered new line, which is not a token, key space, which is also not a token, because white space is new lines, uh, tabs. These are all not considered as tokens because in the syntax tree, it's of no use, right? It has no meaning. But separators have meaning. Then what would we go through? Separators, right? The separators. Then comments also don't have meaning. But in comments, we had to see whether if it is a division operator or not. Yeah, so that's why if it is a division operator, we create it as a token. Just that in separator, instead of separator, there it was, instead of operator, it will be separator for the comma, semicolon, and open and close brackets, right? Here it's operator for division operator, and all of these are for operators. So operators we handled over here, made a token, incremented the tokens array. Uh, Then each digit we handled using the generate number. Then if it is alpha, see for for identifier it has to start with letter, right? So that's what so is alpha. And we have a read identifier which does exactly this L L portion we have done. Now we need to handle L plus D whole star. So any number of letters or digits that has been handled earlier. So how do we do that? We have a is alpha now. So alpha or number we are going to pass. Okay. And we have a buffer. So the buffer size is being there, right? So we are passing in a buffer. So buffer needs to be a array. So buffer length is 32. So the maximum length that we can have in my compiler in my language is that we can have a 32 character long identifier. Okay. So based on that, this L plus T can be handled by is alpha now. So we have a while loop. I remember I told you a while loop can handle this L plus T whole star. Yeah. So it has to be lesser than buffer minus size. Why? Because last we have to append this null character, right? That's why buffer minus size again. And then if ch is yeah, if it is not is alpha now, say we have a plus equal to 10. Okay, so plus is not is alpha now, so we need to unget it, right? So that's what is done here. So here it's not end of the file, right? This plus we haven't reached the end of the file yet. So we have to unget it so that we reparse plus. So for that reason, we'll do unget C and minus the column as well. And we return the length as well because I mentioned it as an integer. Okay. So read identifier. So I have length. And then we check the buffer. We do a string comparison. If the buffer is exit, int, or these keywords, then we define it as a keyword. That is a keyword. Else it's going to be identifier. Okay. So even if I have like as I mentioned, if I have int one, that is also going to be an identifier. Right? So that's why it's been handled earlier. Okay. So, and finally we increment that count and tokens into tokens array, we are going to pass in the token. Okay. And finally, we should not have these, right? See, identifiers cannot be this not identifier in C. So I replicated that here as well. So these are stray. So that's why I'm checking if one of these characters match. I'm going to print out as stray characters. So for example, if I do index this, okay, and if I run this, okay, let's say that I have stray character this one, or if I have what all stray characters did I have? Okay, if I have hash also, if I have tilde also. So if I have tilde, then also I'll have a stray special character. So, so I'm replicating C here, C language stray characters. So that's what is being done here. Uh, okay. And another else case, unrecognized token, as in what all do we have? If we have, uh, say, we have, what do we have? Did I handle tick? So tick is also handled here, right? Hash is handled. Others are all operators. Okay, rest any other ASCII value would be handled here. Okay, any other ASCII character in your keyboard will be handled here. Okay. So basically, our portion, this entire lexical, we have to consider the if part and the else part. Okay, as in like if it is a keyword, we handle that. If it's identifier, we handle that case. If it is an integer literal, we need to handle that case. If it is a separator, we need to handle that. If it is a stray, like here, we need to handle that. And the rest part, the else part, that also we need to handle. Okay. So that's how your automata also works, right? So B star. So ABB is no handled. But for ABA, how do we handle? We need to handle that, right? So that's what the else part here. Similarly, we need to handle here the else part, right? So that's what we're handling the else part. And finally, we'll have the number of token. Okay, number of token count equal to count. If we look at here, we need to pass in it in main.c in Lexer. In Lexer, I had passed this right. So that how I get it by this count rate. See, for each token I'm incrementing, whenever I'm creating a token, I'm incrementing the count rate. So that count value I'm passing it. Okay. So to summarize the entire Lexer is what? It's a finite automata or a regular expression or a regular grammar. Yeah. So we look at new line. If it is a new line, we don't consider it as a token. Okay. So we don't create a token. For space also, we don't create a token. For separator, we need to create a token. Okay. Why we need to create a token? If you look at we are thinking next phase. Whenever we get the semicolon, we understand that it's a statement. So next, after statement one, we have block, right? And after block, we have this again statement four. So statement one, how do we understand statement one ended? Through semicolon, right? So now I had told, right, the statement one, this block and statement four are going to be siblings. So left child, right sibling. That's the concept I used here, right? Left child, right sibling. So that's what. So for syntax phase, this statement ending is determined through the semicolon. That's why semicolon is important, right? So to create that tree, that left child, right sibling, that semicolon is very important. Okay. So that's why semicolon, we created this passing in the value into str val. So again, I had combined into union because I would have integer literal or all of this, right? What all I have? I would have operator, identifier, keyword, all of this are string values. Only integer literal is going to be int. So that's why I'm going to combine it. And if it is an integer literal, it's not going to be a string value, right? So that's why I'm combining it. I'm saving the space there. So why I'm saving the space? So again, if I want to expand this code, my entire compiler project into an embedded system, so I have to save space. So that's why I used unit. So back to this. So this semicolon I have handled, this separator, this comma separator, this closing, this opening, this closing brackets, which are all separators. Then we have this one slash. Slash could be a division operator or a comment. If it's a comment, we don't make it a token. Okay. So if it is not a comment, if it's just a comment, we just pass it and don't make it a token. We don't make it a token. But if it's a division or a division equal operator, assignment operator, we have to pass it and create it as an operator token. So operator token, then we have all other operators. Okay. So the division part is already handled over here, right? And after operator, we have each digit for the integer literal, right? Integer literal, all of this. The hexadecimal digit, the decimal digit, binary, and all of that. So all base cases like the base 2, base 8, base 10, base 10, which is decimal, base 16, which is hexadecimal. So all of this is handled over here. This one is digit, this portion, and uh, and entirely it is handled using generate number, where we multiply the bases and check if it is valid decimal, valid octal, valid binary, or valid hexadecimal. Yeah. Then here combinedly we are checking if it is identifier or a keyword. Then finally we are looking at, see, within this is the keyword part, and within this we are looking into identifier. Okay. So then finally we are looking at stray characters. So stray characters shouldn't be there. So that's why we are outputting as stray character, and for rest ASCII values, we are just printing as unrecognized too. And finally that count we are sending into this one, this number of tokens. Okay. So this is the entire Lexer. So if you run this, right, if I comment out all tokens, if I comment out this one, okay, and let's go through print token. Okay. So in print token, if it is integer literal, and if it is a integer literal token, I'm printing it this way. For keyword this way, for separator this way, identifier this, operator this one, and unknown token. Okay. So let's run we have to run make because I changed the main.c, right? So make, okay, I need to save this file. So if I ready, I have to clean primary make. Then if I run, so let's see. Okay, now, so I'm also printing the line number. The print token. So I'm printing the line. So line we have in token dot line and token dot column, right? How? See here, this line and this column. Okay, that's why I'm getting the line column, line number and column number. So I'm printing that and the token. So for this one, so int x, so int is a keyword, right? So int is print. Then next is x, which is our identifier. Then next we have separator x, this separator as semicolon. Next is int a equals 11. So similarly, finally we have exit, right? At line 14. At line 14 we have exit 100. So exit open bracket. Okay, open bracket is a separator. Exit is a keyword. 100 is integer literal. Then we have closing bracket. Then we have the separator semicolon. Okay. Also for this octal, right? 0100, which is 64. So that is over here. So exit separator is this open bracket. Then integer is 64. Okay. Because this value is 64, right? So I converted it using this base calculation. Remember the base calculation. This generate number, we had this generate number, right? This generate number, generate number, which will internally call this parse number in base. And here the base value is 8. So 8 is passed in, right? So that is octal. So that is octal will have only 0. So we'll come in over here, else if case, and the base is 8. So that is what is passed over there. So the base is 8. Okay. So that is being multiplied. So we get 64. Right? So this value is going to be 64. So that value is 64. Then closing bracket, then semicolon. Okay. So I hope you understood this. So the entire lexical analyzer is finite automata, or you can think it of as a regular grammar or regular expression. So you can see that your theory of computation is very useful over here, right? So this is what I had to cover about lexical analysis, and this how I handle the lexical Lexer part for my language. So I hope you understood. And in the next video, we'll cover about syntax plus semantic. It's going to be a longer one because you need to understand how syntax, how grammar works. Then after that, we need to understand how semantic works. Semantics mainly about variables defined or not. So that portion. So there, simple table plays an important role. So combination of simple table syntax that this grammar. So CFG, context free grammar plays an important role there. So that's it, guys. Then that's it for Lexer. So we'll cover syntax and semantic. Next, we'll cover words, syntax and semantic. Okay. So that's it.